Hybridization of atomic orbitals. So a hybrid orbital is an atomic orbital obtained when two or more non-equivalent orbitals of the same atom combine in preparation for a covalent bond formation. If we look at the most common sp3 hybridization, and we look at CH4 as an example, we're only looking at valence electrons because those are the ones that bond. Carbons occupies 2s2 and 2p1. Since there are 2p2. Since there are two unpaired electrons in the 2p, carbon should only form two bonds, but that's a very unstable molecule. So to account for the four bonds, we can excite one electron from the 2s and place it in the 2p. This gives carbon four unpaired electrons. So if you think about the 2s and the 2p, carbon has two electrons in each. So if we were to excite one of those from the 2s and place it in the 2p, we now have four possible bonding. So hybridization is mixing of the atomic orbitals in an atom, usually the central atom, to generate a set of hybrid orbitals. So if we did bond four bonds to this carbon, the bonds would be different because 2p is different than 2s. So we need to make them all the same so that the bonds would not be different. So carbon forms four identical bonds by mixing the 2s and the 2p. So if we look at the picture, the 2s is a sphere, the 2p is a peanut in shape depending on the axis. So we need to combine these to form the same type of bond or same type of orbital. So down here in blue you can see you have the S and the P mixing together and forming these hybrid sp3 orbitals. Since the new orbitals are made out of 1s and 3p orbitals, they're said to be sp3 hybrid orbitals. So the hybridization is used to describe the bonding scheme only when arrangement of the electron pairs has been predicted by VSEPR. In other words, all tetrahedral shapes are going to be sp3 hybridized. Now, even if it's not tetrahedral because of four atoms, if you have four, which would include a lone pair, you're still going to be sp3 hybridized. So even if it's in the class of tetrahedral, even if taking into account the electrons, it's still going to be sp3 hybridized. So NH3, even though we don't have four atoms, the nitrogen is still sp3 hybridized because of the lone pair needing to be the same as those being bonded. If we look at BCl2, which is linear in shape, one of the beryllium's 2s electrons is permitted to the 2p. So then we have the case of 2s and 2p where we have one electron in each so that we can form our two bonds. The 2s and the one orbital of the 2p mix to form an sp hybridized orbital. So we don't really need these two extra orbitals of the 2p, so they're not hybridized. Just the orbitals that we need are hybridized. sp2 is an example of BF3. So boron promotes one of its 2s electrons to the 2p orbital, mixing a 2s and two orbitals from the 2p. So there's three orbitals for bonding, and we get an sp2 hybridized orbitals. So the concept is not applied to isolated atoms. It's a theoretical model used only to explain covalent bonding. Hybridization is the mixing of at least two non-equivalent atomic orbitals. The hybrid orbital is not a pure atomic orbital, so there is some difference in properties there. The number of hybrid orbitals is generated is equal to the number of pure atomic orbitals that participate in bonding. Hybridization requires an input of energy. However, the system more than recovers this energy during the bond formation itself. Hybridization bonding scheme is within the framework of the valence bond theory, because the electrons in the molecule are assumed to occupy the hybrid orbitals of the individual atoms. So the procedure for hybridizing atomic orbitals. Hybridization simply extends the Lewis theory and the VSEPR model. So you're going to draw the Lewis structure for the model. You're going to predict the overall arrangements of the electron pairs using the VSEPR model. So we're not just looking at atoms, but we're also looking at lone pairs. Then you're going to deduce the hybridization of the central atom by matching the arrangement to those of the hybrid orbitals. So your book has a table, 10.4, which shows the hybridization for each of the different geometries. So if we think about SiBr4, the Lewis structure would be drawn like this. So silicon is in a tetrahedral shape, and because silicon is in a tetrahedral shape, it's going to have an sp3 hybridization. Now another way of determining it is to count the number of things involved. So you have one silicon and four bromines. I'm sorry, you have silicon as a center, and then you have four bromines attached. So you want to look for a hybridization that adds up to 4. 1 plus 3 is 4. So that's a quicker way of doing the hybridization instead of having to simply memorize all the time. For BCl3, you have to remember that boron doesn't need a full octet. It only needs 6 valence electrons, so its geometry would look like this, and it would be trigonal planar. So its hybridization would be sp2. Again, you have 3 things around the boron, so 1 plus 2 is 3. Now you can have an extended octet or expanded octet. So you need to hybridize with the sp and the d orbitals. So when molecules break the octet rule or have expanded octets, we have to use sp and d orbitals to combine to allow for so many bonds. S and p are only good up until 4 bonds. Past that, you have to have d orbitals. So we're talking about the elements in row 3 and 4, 5, and 6. So describe the hybridization state in SEF6. So we would draw our structure. And we can see that selenium is going to break the octet rule. It has 6 things around it, so we want our exponents to add up to 6. S is 1, P is 3, so I'm at a total of 4, but I need 6. So then we can use 2 of the d orbitals to make 6 identical orbitals for bonding. So selenium has a hybridization of sp3d2. Now some textbooks have it d2 sp3. Either way of writing it is appropriate. Hybridization in molecules containing double or triple bonds. So if we consider C2H4, and let's draw the structure, C2H4, evenly distribute the hydrogens. Remember, carbon has to have 4 bonds. It only has 3 right now, so there has to be a double bond there. It's going to be trigonal planar in geometry. So my carbon, each of my carbons actually have a trigonal planar shape to them. So each carbon has to be sp2 hybridized. The 2px and the 2py, those 2 orbitals from the 2p, combine with the 2s orbital to form our hybrids. That leaves our 2pz orbital unchanged. The 2pz orbital is perpendicular to the plane. So if we look at the picture here, these green orbitals are my hybridized orbitals forming the bond. So this is bonded to hydrogen, this is bonded to hydrogen, and this would be bonded to carbon. So the 2pz is perpendicular. That means it can form another bond with the carbon on this side by overlapping sideways. In other words, This carbon over here also has a 2pz that is not being hybridized, and so we can form another bond there. So you have your one bond there, and then you have a double bond. So the double bond is not made up of identical bonds. The 3 bonds formed by each carbon are all sigma bonds, and the second type is called a pi bond. Sigma bonds, the covalent bonds, are formed by orbitals overlapping end to end. The electron density then is concentrated between the nuclei of the bonded atoms. So in our picture, in letter A, we're seeing just the sigma bonds. They're overlapping bonds, so they are all sigma. Now the symbol for sigma is like an O with a little swoosh at the top. A pi bond is a covalent bond formed by sideways overlapping orbitals with electron densities concentrated above or below the plane of the nuclei. So in picture B, that 2pz that was not hybridized is overlapping. So this would be our pi bond. If we put them all together, this is what the structure would look like. You have your 2 carbons, you have the sigma bond, and then you have a pi bond. We do draw the pi bond on top and below because we're not sure where exactly that bond is occurring. Some people say that it flips back and forth between the 2 lobes of the 2p orbital. So you have a double bond there, and then you have single bonds to the hydrogens. So in C2H4, we have a total of 5 sigmas and 1 pi bond. It's the pi bond formation that gives ethylene its planar geometry. Even though the double bond is usually shown as 2 identical lines, it's not identical. The pi bond actually has a lower bond enthalpy than the sigma bond. So there is a difference between the 2 lines that we draw when we draw a double bond, but it's easier just to draw them equal to each other. So these 2 pictures, again, are just showing you that the pi bond is outside of the plane where the sigma bonds are all in the same plane. And then we have the electron density structure. Notice that the inside the plane is where electrons are being, or is where the more positive is, and then the pi bonds coming off of there, not in the plane, are where the negative is drawn. C2H4, if we draw that real quick, actually contains a triple bond. Oops, you have to evenly distribute our hydrogens here. So the carbon having to have 4 bonds would have to have a triple bond. So the carbons are 1, 2, sp hybridized. So there are 2 pi bonds formed by the sideways overlap of the unhybridized 2py and 2pz orbitals. Thus the triple bond is 1 sigma and 2 pi's. So the sigma again is the overlapping hybrid, and then we have 2 options for overlapping unhybridized 2p orbitals. So that's where we have our other 2 lines drawn. And then you have your space filling diagram over here. So you have a pair on the top and the lobes on the bottom to represent your unhybridized orbitals. And then you can notice again that the electrons in the electron density diagram would be where those pi bonds are located. So even though we draw those 3 bonds identical, they're not identical. 1 is sigma, 2 are pi. So if we look at hydrogen cyanide, which is HCN, describe or assume that nitrogen is sp hybridized. Describe the bonding. So our diagram would look like this. So our carbon would have to be sp1, 2 hybridized, and our nitrogen, 1 from the lone pair, 2 from that carbon, is also sp hybridized. So the carbon would be contributing the 2s and 1 of the 2p. to form a bond with hydrogen and nitrogen, but it has to be hybridized to a 2sp orbital so that we can form identical bonds. The nitrogen is going to do the same as well. It's going to have a 2s and one of its 2p's, and it's going to combine them to 2sp so that the bond and the lone pair are identical. That leaves us with 2 pi bonds being able to form. So we're not using all of the p orbitals, we're just using one of them. So the other 2 are able to be perpendicular to that sigma bond and form our triple bonds.